This is the video for part 2 of section 8.1, Congruence and Lagrange's theorem. In this video, we're going to examine the problem of the structure of finite groups. One of the major problems in group theory is the classification of all finite groups up to isomorphism. This would be a list of groups such that every finite group is isomorphic to exactly one group on the list. While this general problem is still unsolved, there are many partial results classifying groups with certain properties. For instance, Theorem 719 provides a classification of cyclic groups. Every finite cyclic group is isomorphic to z sub n for some positive integer n. Lagrange's theorem and its corollary are the primary tools used to classify groups. We'll use them below to classify groups of prime order and groups of orders 4 and 6. So first we have Theorem 8.7, which says let p be a positive prime integer, and then every group of order p is cyclic and hence isomorphic to z sub p. So let's suppose G is a group of order p. We need to show that G is cyclic. Suppose A is any non-identity element of G. We want to show that G is equal to the cyclic group generated by A. Now, since A is not equal to the identity, then the order of the cyclic group generated by A is not 1. By Lagrange's theorem, the order of this subgroup must divide the order of G, which is P. Now, since P is a prime, then the order of the cyclic subgroup must be P, which implies that G is equal to that cyclic subgroup generated by A. Therefore, G is cyclic, and by Theorem 719, G is isomorphic to Z sub P. The next two theorems classify all groups of order 4 and of order 6. So first we have Theorem 8.8, which says that every group of order 4 is isomorphic to either Z sub 4 or Z2 cross Z2. So let's suppose G is a group of order 4. By Corollary 8.6, the corollary to Lagrange's theorem, the orders of the elements of G must divide the order of G, which is 4. So the non-identity elements must have order 2 or 4. Now, we can then consider two cases. G has an element of order 4, or G does not have an element of order 4. So case 1, suppose G has an element A of order 4. Then the cyclic subgroup generated by A has order 4, so G is equal to that cyclic subgroup, and by Theorem 719, G is isomorphic to Z4. For case 2, we'll suppose that G does not have an element of order 4. And let's suppose that G is equal to the set containing the identity E and 3 other elements A, B, and C. Then A, B, and C, the non-identity elements, all have order 2, since G has no element of order 4. It follows that the operation table of G is as follows. So we have our 4 elements across the top and on the left, and we have the first row and column filled in, and each element has order 2, so A squared is equal to E, B squared is equal to E, and C squared is equal to E. Now we want to fill in the remaining entries. We can use the fact that each element appears exactly once in each row and in each column of the operation table. So then, looking in the second row, AB, the third element in the second row, must equal either B or C, since we already have an A and an E in that row. However, B already occurs in the third column, so AB has to be equal to C. Since B is the only element that does not yet appear in the second row, then our fourth entry, AC, must be equal to B. Looking in the third row, BA, the second element, must equal either A or C, since B and E already appear in the third row. Since A already occurs in the second column, then BA is equal to C. And then our fourth entry, BC, has to be equal to A. And then once we're down to the fourth row, the elements or the remaining entries are determined. So that gives us our operation table. We now want to show that G is isomorphic to Z2 cross Z2. So we'll define a function f from G to Z2 cross Z2 by f of the identity is equal to the identity in Z2 cross Z2, 0, 0. F of A is 1, 0, f of b is 0, 1, and f of c is 1, 1. Then f is clearly a bijection. It's a one-to-one correspondence between the two sets. To show that f is a homomorphism, we can start with the operation table for G. We'll apply f to each element in the operation table. And we'll substitute for the function values in Z2 cross Z2. So f of E is equal to 0, 0. F of A is equal to 1, 0. F of B is equal to 0, 1. And f of c is equal to 1, 1. Now, examining this table, you'll see that the result is the operation table for Z2 cross Z2. So this shows that f is a homomorphism. It preserves the operations, and hence is an isomorphism. And thus, G is isomorphic to Z2 cross Z2, and this proves case 2 and completes the proof of the theorem. So every group of order 4 is either isomorphic to Z4 or to Z2 cross Z2. Next, we have theorem 8.9, and this tells us that every group of order 6 is isomorphic to either Z6 or S3, the symmetric group on 3 elements. So let's suppose that G is a group of order 6. By corollary 8.6, the corollary to Lagrange's theorem, the orders of the elements of G must divide the order of G, which is 6. So the non-identity elements must have order 2, 3, or 6. We can then consider two cases. G either has an element of order 6 or G does not have an element of order 6. So case 1, we'll suppose G has an element A of order 6. Then the cyclic subgroup generated by A has order 6, so G is equal to that cyclic subgroup. And by theorem 719, that tells us that G is isomorphic to Z6. For case 2, we'll suppose G does not have an element of order 6. Then every non-identity element of G has order 2 or 3. We want to show that G must have an element of order 3. To show this, we'll use a proof by contradiction. So let's suppose G does not have an element of order 3. Then every non-identity element must have order 2. That's the only option left. We want to then derive a contradiction. Since every non-identity element has order 2, then every element is its own inverse. And by a homework exercise, this result implies that G is abelian. So let's suppose that C and D are two distinct non-identity elements. Then CD has to belong to G. Since G is a group, it's closed, and CD cannot be equal to the identity since C and D are not inverses of one another. C is its own inverse, and D is its own inverse. So let's let H be the set containing E, the identity, C, D, and the product CD. Now, since G is abelian, and every element in G has order 2, then C squared is equal to the identity. C times CD will be C squared times D, which is just going to be D. D squared is equal to the identity. CD times D will be CD squared, which will be just C. And CD, quantity squared, since it's not equal to the identity, has order 2, so CD squared is equal to E. This shows that H is closed. Every possible product is contained in H and contains inverses of each of its elements. It follows that H is a subgroup of G. However, the order of H is 4, which does not divide the order of G, which is 6, so this contradicts Lagrange's theorem. So this contradiction arose from supposing that G did not have an element of order 3. So therefore, G must have an element of order 3. So let's suppose that A has order 3. And let's let N be the cyclic subgroup generated by A. So N will be the identity, A, and A squared. Let's let B be an element of G that is not in N. Since B does not belong to N, then the cosets NE, which is just N, and NB, which is B, AB, a squared b are not equal, so they must be disjoint. That's a property of cosets. Two cosets are either identical or disjoint. So this gives us 6 elements in our group G, which only has 6 elements. So these cosets must contain all the elements of G, so we can write out G will be E, A squared, B, AB, A squared B. These are all the elements of our group G. Now we next want to show that the element B has order 2. To show this, we'll use another proof by contradiction. So let's suppose the order of B is not 2. Then B squared is not equal to the identity, so B squared must be one of the other elements in the group. So it's either A squared, B, AB, or A squared B. We need to derive a contradiction in each of these 5 cases. Now note that since the order of B must divide the order of G, which is 6, and G does not have an element of order 6, that's what we're assuming in this case, then the order of B must be 3 if we're supposing it's not 2. So let's suppose that B squared is equal to A. That's our first case. Now multiplying both sides by B on the right, we obtain B cubed equal AB, which is a contradiction since B cubed is the identity, but AB is not. So our next case is suppose B squared is equal to A squared. Multiplying both sides of this equation by B on the right, we obtain B cubed equals A squared B, which is again a contradiction since B cubed is the identity, but A squared B is not. Third case, suppose B squared is equal to B. Canceling B from both sides, we obtain B is equal to the identity, which is a contradiction. Our fourth case is suppose B squared is equal to AB. Canceling B from both sides here, we obtain B is equal to A, another contradiction. And our fifth and final case, suppose B squared is equal to A squared B. We can cancel B from both sides once more, and we obtain B is equal to A squared, again a contradiction. So we obtain a contradiction in each of these 5 cases, and so this shows that our element B has order 2. So B squared is equal to the identity. Next, we want to determine the product BA. We want to show that BA is equal to A squared B. To show this, we can use another proof by contradiction. So let's suppose that BA is not equal to A squared B, so BA must be one of the other elements in the group, either E, A squared, B, or AB. So we again have 5 cases, and we need to derive a contradiction in each of these 5 cases. So let's suppose that BA is equal to the identity. This implies that A and B are inverses of one another, so in particular A is equal to B inverse, which is equal to B. That's a contradiction. For the second case, suppose BA is equal to A. Canceling A from both sides, we obtain B is equal to E, another contradiction. Our third case is, suppose BA is equal to A squared. Canceling A from both sides, we obtain B is equal to A contradiction. Our fourth case is, suppose BA is equal to B. We can cancel B from both sides here, and we obtain A is equal to the identity, another contradiction. And our fifth and final case is, suppose BA is equal to AB. Then, by a homework exercise, since A and B commute, the order of AB is the least common multiple of the order of A, which is 3, and the order of B, which is 2. So that tells us that the order of AB is equal to 6. Now that homework exercise actually was from section 7.5, and it was talking about cycles, but the result still holds even if we're dealing with elements in a general group. So we have an element AB of order 6. Well, this is a contradiction since we suppose that G does not have an element of order 6. So therefore, BA must be equal to A squared B. We now have our group G consist of the elements E, A squared, B, AB, A squared B, where the order of A is 3, the order of B is 2, and BA is equal to A squared B. Using this information, we can determine all the entries in the operation table. So we'll start by setting up the table. And the first row and first column entries are just going to be the entries from the table border. So we get those filled in. And the second and third row entries follow immediately from the form of the elements in G and the fact that the order of A is 3, so that tells us that A cubed is equal to the identity. So for instance, in the second row, our second element is AA, which is just A squared. Our third element is AA squared, which is A cubed, which equals the identity. The fourth element is just AB. The fifth element is A squared B. And the sixth element is A times A squared B will be A cubed B, but A cubed is the identity, so this will be B. In the third row, the second entry is A squared times A, that's A cubed, which is the identity. The third entry is A squared is A to the fourth, which is going to be A, since A cubed is the identity. And then the fourth entry is A squared B. The fifth entry is A cubed B, which is just going to be B. And the sixth entry will be A to the fourth B, which will be AB. So that fills in the second and third rows. And so now we've just got the fourth, fifth, and sixth rows to contend with. So in the fourth row, the second entry is BA, and we already showed that that's equal to A squared B. The third entry in the fourth row is going to be BA squared, and this can be written as BA times A, and we have that identity for BA, that's A squared B times A, and this is A squared BA, and again substituting from our identity, BA is A squared B, so this will be A squared B, which is A to the fourth B, and A to the fourth is just A, because A cubed is the identity. So this is AB. So that's a little bit of work, but that gets us the third entry in the fourth row. Now the fourth entry in the fourth row is going to be B squared, which we know is the identity. The fifth entry will be B times AB, which is BA times B, which is A squared B times B, using the identity. And this is A squared, and B squared is equal to the identity, so this is just A squared. So that entry is A squared. Now we can calculate the remaining entries in the table in a similar manner. Okay, we can sort of apply our identity repeatedly. So what we'll obtain is an A for that last entry in the fourth row, and then in the fifth row we obtain these elements. And in the sixth row, these entries. And that gets us our operation table. We now want to show that G is isomorphic to S3, which is the symmetric group on 3 elements. And so this consists of the identity permutation, and then 2 3 cycles, 1 2 3, 1 3 2, and 3 2 cycles, 1 2, 1 3, and 2 3. To show this, we need to find an isomorphism F from G to S3. Since an isomorphism must preserve the order of elements, then F must map A, which has order 3 in G, to an element of order 3 in S3. So this will be one of the 3 cycles. F must also map B, which has order 2 in G, to an element of order 2 in S3. So this will be one of the 2 cycles. So we're going to define F from G to S3 by, well, F maps the identity to the identity, so F maps E to the identity permutation 1. And then F maps A to one of the 3 cycles, and so we'll just pick 1, 2, 3. And then F of A squared will actually be the other 3 cycle, 1, 3, 2. Now F of A squared will have to be F of A quantity squared, so that will be the 3 cycle 1, 2, 3 squared, which is 1, 3, 2. So once we define F of A squared is determined. And then F of B will map to one of the 2 cycles, so we'll pick 1, 2. And F of AB will map to another 2 cycle, 1, 3, F of A squared B to our remaining element, 2, 3. Then F is clearly a bijection. It's a one-to-one correspondence between our 2 sets. And to show that F is a homomorphism, we can use the operation table, just as we did in the previous theorem. So we'll start with the operation table for G. and we'll apply f to each element in the operation table. And we'll substitute for the function values in S3. We'll do it one element at a time. So f of e is equal to the identity permutation 1. So we'll replace each element in the table f of e that's labeled f of e with 1. And then f of a is the 3-cycle 1, 2, 3, so we'll replace each of those elements with 1, 2, 3. F of a squared is the 3-cycle 1, 3, 2. We'll replace each of those elements with 1, 3, 2. F of b is the 2-cycle 1, 2. F of ab is the 2-cycle 1, 3. And finally, f of a squared b was defined to be the 2-cycle 2, 3. And so there's our operation table after starting with the operation table for G and replacing each element with its image under the function f. Now, if you examine this table, this result will be the operation table for S3, and so this shows that f is a homomorphism. The operations are preserved, and hence f is an isomorphism. And thus G is isomorphic to S3. And this proves case 2 and completes the proof of the theorem. Now, these last 3 theorems provide a complete classification of all groups of order less than 8. So we can set up a table with the order of each group G and what G is isomorphic to. So if the order of G is 2, G is isomorphic to Z2. If the order of G is 3, G is isomorphic to Z3, so both 2 and 3 are primes. If the order of G is 4, then we've shown that G is isomorphic to either Z4 or Z2 cross Z2. If the order of G is 5, well, 5 is a prime, then G is isomorphic to Z5. And we've just got done showing that if the order of G is 6, then G is isomorphic to Z6 or S3. And if the order of G is 7, then G is isomorphic to Z7. 7 is a prime. Now, this particular list has been extended much further. As the order increases, there may be more non-isomorphic groups of a given order, and much more work required to characterize the groups. So just characterizing a group of order 6 was quite a bit of work. So it gets to be much more work as the order gets larger. For instance, there are 5 non-isomorphic groups of order 8. 14 of order 16, and 267 of order 64. So you can imagine looking at a group of order 64 and trying to classify it as one of these 267 different groups. Okay, so this finishes off the lecture for part 2 of section 8.1, and this finishes off our section 8.1 and finishes off our course.